All right, so today we're going to go ahead and dive more, much more into kernel thread implementation details. You'll find that over the next few lectures, we'll probably get really technical really quickly, and we'll sort of go up and down because obviously there's a lot of theory underlying, the way that these things are designed, but then there's a lot of technical details because it's a freaking operating system. So what can you do? Anyway, so we started talking about kernel threads. Remember, we just introduced this notion that the kernel needs some kind of multitasking primitive. And it turns out that this is the thing that is scheduled as well. So kernel threads are what the scheduler actually schedules. And it looks at how they behave. And obviously, the process is associated with the kernel thread. So the process's behavior affects the kernel thread's behavior and so forth. So the kernel thread is a minimal schedulable task inside the kernel. And they do tend to be very lightweight. So they have the minimal CPU state, program counter, other registers, the general purpose registers, flags register, and stack pointer. Obviously, along with this stuff is a stack. So that tends to be all that's in these kernel threads. Maybe a few pointers to other things as well. And like I say, it corresponds to a user mode process, but it isn't the user mode process. It's the thing in the kernel that handles issues that the process might need to deal with. Okay, so I make a system call, I trap into the kernel. The process's corresponding kernel thread is the thing that does the work. And so there's a process control block or some kind of task struct or process struct that's associated with that kernel thread. And that is the thing that keeps track of all of the resources that the user mode process holds on to. Why do we have this separation? Well, it should become quickly comprehensible as we go into how these things are utilized. Okay, we do want to stay inside the kernel for a short time, not a long time, because it means we're not doing work. We're not doing useful work. We'd like to get back to the user program. So kernel threads end up having a pretty small stack. And here's a few examples. Like Linux, at least 32-bit Linux, has about 8 kilobytes for kernel thread stacks. I mean, it's a little bit less. Let me see. It says there 8140 bytes. Because the thread info struct for keeping track of the kernel thread is also in that 2 pages of space that's allocated for each kernel thread. Okay? And so you have the kernel thread stacks, starts at the top of this chunk of memory and grows downward, and then the thread info structure is at the bottom, and it points to other important details. And you can see the process descriptor points back to the kernel thread thing that actually corresponds to the process. And then this also keeps track of, somewhere in here, we'll talk about where in a moment, we keep track of a stack pointer, and that obviously indexes into the kernel thread stack because that's where the stack pointer should resume when the kernel thread resumes executing. Okay, so Windows has a couple of different sizes on IA32, 12 kilobyte kernel stacks on x86 64. Since pointers are larger, things are larger, we have a little bit more space, so 24 kilobyte kernel stacks. Pintos has 4. And you might say, wow, that seems really small. And if you've done any reading about the threading assignment, then you probably have already come across the commentary that says, Pintos tries to detect if you overflow your thread stack. It can't do a perfect job of this. And so you might find yourself in La La Land, which is always a fun place to visit. Hopefully not for very long. But it turns out that this is generally fine. Okay, but it is a limited amount of space. It's way more limited than we have for applications. And so we have to program in a correspondingly careful way because we have limited resources here. Kernel control path. Okay, so this is the thing that actually handles stuff in the kernel on behalf of some other thing. Be it a user mode process, be it a hardware device that decided it wanted to interrupt what's going on. So kernel control path starts with a trap, or it starts with a fault, or it starts with an interrupt, and it executes to handle some task within the kernel. We say that kernels are reentrant if we allow kernel control paths to overlap. So if you're ever wondering, okay, what is a reentrant kernel? We're going to talk about some of those things today. If you allow kernel control paths to overlap, then you now have a reentrant kernel. Almost all operating systems that are interesting have reentrant kernels because it's really common and really easy to have overlapping kernel control paths. I'll give you a really simple version that you're going to run into when we finally get to virtual memory, and that's Project 5. So the program makes a system call, I want to read a big chunk of a data file, or I want to write a big chunk of a data file, and let's say that there's strong memory pressure in the operating system at that point. So some of those pages have been paged out, or maybe we're allocating space on the heap and nobody's touched a page yet, so we haven't actually allocated a page for that region of memory yet. So the program makes a system call, passes pointers to memory areas, and inside that kernel trap handler, we generate a page fault. It happens all the time. So the kernel control path has to be interrupted by the page fault handler, which steps in and tries to do the things that are required to resolve the page fault. Okay. Now, like I say here, it performs disk accesses. What really happens is it starts disk accesses, which then need to execute for, let's say, I don't know, 10 million clocks, something like that. If we're really slow, maybe we're lucky and we have a solid-state drive, and it might be tens to hundreds of thousands of clocks, so we're a little bit faster. So we have some time to do other things, and so we switch to another kernel control path. Okay. It's also very common, let's say that I'm inside said disk access, and I'm performing some operations on behalf of a process, and a timer interrupt goes off, or a keyboard interrupt goes off, or something like that. So you can see that it's pretty easy to have overlapping kernel control paths. So of course, since these things can overlap, we have to make sure that we don't corrupt shared state. And like I say here, it's not really possible to make everything reentrant. And really what we mean by that is to localize state in such a way that we can call this thing multiple times overlapping, no big deal, nobody cares. We have shared state. Operating system kernels manage a lot of shared state. Two processes open the same file. There's shared state that's being manipulated. We talked about all of those kinds of things early on in the class. So you can see that if we can't really manipulate, we can't localize state to a particular kernel control path, then clearly we need some kind of synchronization mechanisms to make sure these things don't step on each other's toes. So we'll talk about that a lot next time, and on Friday we're going to have a fun lecture and actually talk about one of the most recently adopted and most widely, I should say it's becoming very widely used, and it's a very innovative approach to synchronization called read, copy, update. I wanted you guys to actually see it and talk about it because it's cool and complex, and we're Caltech, so we should. So, but anyway, you can see here, we have to know what kernel paths can overlap, when they can overlap, and where they overlap. So these are the things we need to understand, because we can't just throw locks at problems and hope it solves the problem. I don't know if I'm not going to ask for a show of hands, but if you've ever tried that, you've probably been frustrated. I worked at a company one time where there was this guy, we were working on a Java application server. Again, lots of synchronization fun in that. And something was deadlocking or not being protected properly, so it was generating spurious results. And so he's like, well, maybe I need to have another lock to guard the lock that I'm trying to acquire. And I'm just sitting at my desk shaking my head because I knew that this would not solve the problem. That's not an approach to solve problems. You need to understand it, understand what can overlap, where can they overlap, where are they manipulating shared state, and then you know where to place locks. And we also, so we have to understand how to achieve synchronization in various scenarios. We'll talk about that a lot as we go through the course. Here's a really simple example. What kernel control paths are allowed to block? What do we mean by blocking? We've talked about that a lot in various classes. You probably intuitively understand if you don't have some kind of formal definition of it. What we mean is that we can suspend the execution of that control path, be it a kernel control path or some logical flow within a program or something like that, but we can suspend it and go do other things. So it's passively waiting, and then we can come back to it later. Hardware interrupts are never allowed to block. They're not allowed to stop doing what they're doing and passively wait for something else because they have to run to completion. They're holding the processor. They're keeping the processor from being utilized by anybody else. So hardware interrupts are a great example of something that must be executed to completion. We can't suspend it and make it passively wait. Now, there's a lot of little subtleties to that statement. We'll talk about a couple of them today because Linux has a really neat way of handling interrupts. It's actually pretty representative of a lot of operating systems. But the consequence of this constraint that you cannot have an interrupt handler block is that it cannot acquire a lock to guard shared state. Because if it has to acquire a lock, then it has to potentially wait for somebody else to release the lock, which means it would passively wait and be suspended. Okay? So interrupt handlers are not really allowed to do this. This is a pretty important thing. We need interrupt handlers to behave in a way that allows them to progress all the way to completion. Yeah, question, comment?
What if it tries to get a lock without blocking?
Yes, what if it tries to get a lock without blocking? This is a very interesting one. So let's say it tries to acquire the lock, and if it can't, it just continues on. It says, I tried, I'll just let this be handled the next time. That would be perfectly fine. The interrupt handler is allowed to progress to completion. You just need to make sure it's okay for that interrupt not to be handled. So that's one example. There's another example which is really interesting, which is the use of spin locks on a multi-core system. So I have a situation where let's say I have 4 cores, and all 4 cores periodically have a timer interrupt, and they go look at some shared state. Okay, well, those timers may or may not be synchronized with each other as they're going off. One processor's interrupt goes off, it enters the timer interrupt handler, and it wants to manipulate the shared state. Well, it can spin lock. It's not allowed to passively wait, but it can actively wait. So it tries to spin lock on some, spin lock, and to acquire access to the shared data structure. Some other processor may actually have that lock on that shared data structure, but it's also allowed to progress to completion. So at some point, it will release the lock. Somebody else who's actively waiting is allowed to acquire it and continue on. That is one of the very few situations where interrupt handlers are allowed to acquire locks, but they cannot passively wait. They must actively wait. Okay? Any other questions? Yeah.
Why is actively waiting better than passively waiting?
Because the interrupt handler is not allowed to passively wait. Yeah. It's just a constraint of the way the system behaves. The interrupt handler must execute until it hits that IRET, and then it gives back the processor to whoever it interrupted, and it's not allowed to just suspend. It's not allowed to do that. Okay, so if you have things that you're doing in interrupt handlers and you want to make sure that they can't garble shared state, then the only thing you can really do is turn interrupts off. Okay? And we want to do this as infrequently as possible because then that starts increasing the latency of handling interrupts, and it makes users grumpy because their systems start behaving slowly, or they perceive it and then they get grumpy. There's often times where you can't do this either because if you're on a multi-core system, you can turn off your interrupt dispatch, but you can't turn off everybody's interrupt dispatch. Okay? So you have situations where you have to spin lock on multi-core systems. This is the kind of thing where I would love for you to have this experience in this class, but Pintos is not designed to be a multi-core operating system, so you kind of can't. If you want to do like a special project on your own, you could explore adding multi-core support to Pintos. I think it'd be challenging, but I think you could probably do it if you start with the basic initial version of Pintos and added multi-core to it and took it from there. Okay, so we say that kernel control paths execute in specific contexts, which basically dictate whether or not they're allowed to block. So if we're running on behalf of a process, we say it's in process context. So the kernel is executing, we're inside an interrupt handler of some kind, maybe it's a trap handler, maybe it's a fault handler, but we're allowed to block because we're executing on behalf of a process, and if the kernel thread blocks, the process also blocks. Okay, so that's allowed. If we're in process context, we're allowed to acquire locks that make us passively wait. We're allowed to block. Trap handlers basically always run in process context because they can do things that block or cause context switches. That's perfectly allowed. Fault handlers typically run in process context. Now that's kind of an interesting thing. There's some implications of the statement that fault handlers typically run in process context. Okay. What if I'm in my timer interrupt handler and I generate a page fault? Well, I can't sit around in my timer interrupt handler and wait for that page fault to be resolved. I have to get out of it so I can go do other things. So you can see that fault handlers basically should never be triggered by interrupts, hardware interrupts. We have to be very careful to avoid that kind of thing. So like I said, the kernel code was invoked by a hardware interrupt handler, then it's running in interrupt context, and we're not allowed to block. So we have to be very careful that if we're in interrupt context, we can't block. If we're in process context, we can block. Okay? You'll run into these kinds of things in PinToS, but thankfully it's sort of the simplest version that's interesting. So you won't get into some of the really hairy stuff that you can run into that we'll talk about a little bit today. Okay, and so again, a consequence of this is that your hardware interrupt handler should basically never block. They should basically access pages of memory that are locked into physical memory somewhere so that they can't be paged out. The operating system kernel needs to be very careful about what it's allowed to page out, what it's not allowed to page out. And if they do page fault, it's probably indicative of an operating system bug because you're causing an event that can block, that does block usually, and the hardware interrupt handler shouldn't do anything that really can block. Okay? Any questions? These are the constraints. Now, again, you say, well, do we really have to follow these constraints? Well, I suppose you could design an operating system where you didn't follow these constraints. It would be very complex. Most operating systems do not try to move without, outside of these bounds. Okay? You do have paged kernels where parts of the kernel are allowed to be paged. Parts of the kernel are locked in the memory so that they cannot be paged out, like the page fault handler. That's a really bad thing to have page out. Okay? There's a few other things that you're not allowed to page out. Core critical kernel data structures will not be allowed to be paged out. The operating system has control of that stuff, so it just makes sure that it won't ever occur. Okay? It will be more like process data structure related stuff that can be paged out. Okay, so here's another question. Are interrupt handlers allowed to overlap? Okay, well, again, this is pretty common to allow interrupt handlers to overlap. We generally allow software exceptions to be interrupted by hardware interrupts. That's no problem. All we're really saying here is that the kernel's reentrant. Remember, I have a system call. The system call accesses memory that generates a fault. Okay, I've got to resolve the fault. Now I have a fault handler overlapping a trap handler. No big deal. This is what we already talked about. Okay? But what about if I have a timer interrupt go off during the fault handler? Should I allow the timer interrupt handler to interrupt the fault handler so that now I have trap, page fault, timer interrupt? Should I allow those situations? So this is another kind of question that operating systems have to answer. Okay, so hardware interrupts aren't allowed to overlap other hardware interrupts by default. We can always change this because we control the hardware. So there's two mechanisms on IA32, which PinToS uses both of, so that hardware interrupts are not allowed to interrupt other hardware interrupts. The first one is that interrupts are automatically disabled in the delivery of an interrupt. Okay, so when IA32 dispatches a hardware interrupt, remember it pushes stuff onto the stack where it interrupted. You can never interrupt in the middle of an instruction. The interrupt line can go active and say, hey, there's an interrupt to be delivered, but the processor won't deliver it in the middle of an instruction. It's nice that way. It always happens between instructions. And so as the interrupt is delivered, one of the things that happens is the flags register is saved, but the interrupt flag is cleared. So all maskable interrupts are disabled when you enter into the interrupt handler. Okay? You can turn it back on if you want. But as long as you don't, then hardware interrupts can basically never overlap each other. Okay? So that's the first mechanism, keeping hardware interrupts from overlapping. The second one is something that you probably are familiar with if you did the second project the way you were supposed to, because interrupts need to be acknowledged on the interrupt controller before it will deliver that kind of interrupt again. If you look at the OS Dev wiki, there's like tons of forums where people are like, I got one key press and I can't get any more key presses. Well, the reason why is because you forgot to acknowledge the interrupt at the end of your interrupt handler. Okay? So the APIC is the same as the PIC in that you have to acknowledge the interrupt that you handled before another one will be delivered. So if you do that at the end, you basically will never end up with multiple occurrences of the same interrupt overlapping. Okay? So Pintos actually constrains both of these things. So if you're sitting down and trying to figure out, okay, I have this page fault handler and my program is exploding and I don't know why. That probably won't start happening until Project 4 because that's where you start caring about page faults. So you say, well, could it be something happening in my timer? Well, no, because they're not allowed to overlap. That was easy. Okay, so you can think about those kinds of things and figure out what things may overlap, what things can interrupt what state do I then need to protect to make sure that I don't run into state corruption. Okay, any questions about this? Okay, so that's that. Yeah, so more advanced operating systems will actually allow you to re-enable some interrupts so that they can interrupt other things. Okay? And it depends on what they want to accomplish. We'll start touching on a few of those things as we go through this discussion. But you can imagine if you don't have the need to, to re-enable hardware interrupts while you're inside of a hardware interrupt handler, don't turn it on. Just leave it off. Get out of your interrupt handler as quickly as possible so your system is performant, but don't allow them to overlap. It's simpler. Okay, so Linux has 3 different kinds of interrupts that it cares about. This is how Linux categorizes interrupts. You have critical interrupts, which have to be handled right away, and they're fast. So the handler actually runs with all other interrupts disabled. Those are critical interrupts. So these are the ones that are handled. No other interrupts are allowed during that time. Get them done, get them handled, and then go back to whatever you were doing. Non-critical interrupts are short, so you can finish them quickly, but other interrupts are allowed to interrupt them. Specifically, critical interrupts, obviously, would be allowed to interrupt them. And I suppose that if you had other non-critical interrupts, which were a higher priority, then those could also interrupt another non-critical interrupt. Okay? And so how do we enforce this distinction? Well, it's just how we write the program, right? If we never say STI in our interrupt handler so that interrupts are turned back on, then we have an interrupt handler that won't be interrupted. If we have a non-critical interrupt handler, we can just turn on interrupts where we want to and allow other things to trigger. Then you have the third one, which I think is actually the most interesting, which are non-critical deferrable interrupts, where basically all you want to know is that it happened and you want to do something about it eventually, but you don't care about doing it right away. Those are non-critical deferrable interrupts. So we may have a task that shouldn't actually be in the interrupt handler. And so they kind of behave exactly as you would expect. You go ahead and acknowledge the interrupt right away so that you don't miss any subsequent interrupts of that type. And you do this magical little thing where you squirrel away a little callback function that says, handle this situation when you get a spare moment. That's basically how non-critical deferrable interrupts are handled inside of Linux. Yes?
Do you have any examples of what things would go in those?
You know, I don't, and I really wanted to look that up, but I was too lazy. So this stuff is talked about in great detail in the inside the Understanding the Linux Kernel book. So I'm hopeful that it actually gives examples of these various kinds of interrupts. I would imagine that a good example of a non-critical deferrable interrupt would be page fault handling. But I couldn't tell you off the top of my head, like maybe a timer interrupt would be a critical interrupt. There's other things Linux does that really complicate stuff that we'll talk about in a second. But yeah, I should go and look up some examples of each of these just to illustrate. Okay, so yeah, I apologize that I don't have an answer right now, because that would be a good thing to share. So the way that Linux handles these non-critical deferrable interrupts is using this mechanism called soft IRQ. Again, if you've done any heavy Linux administration or anything like that, you may have come across this. There's actually this little daemon that runs soft IRQs in the background if they don't get handled some other time. But basically, the idea is we create what they call a deferrable function. It's kind of just a closure. Okay? We have a function callback. We have some environment that's necessary for the function to know what it's supposed to do, and we queue that up somewhere to be executed at some point in the future. It doesn't have to happen right away. Okay? But notice the interrupt handler itself runs to completion really quickly. Create a soft IRQ, acknowledge the interrupt, return. That's all it has to do. And then we go ahead and run the deferrable function later. So they are run as a batch, typically. So they queue up and then we run them all as a batch. And it can either happen at the end of some other I.O. operation. So when an I.O. interrupt occurs, then we say, oh, we may have other things that need to be done. So we can go ahead and run soft IRQs if there are any pending. And then there's also K soft IRQD, which I have listed here, which if you don't have any I.O. operations occurring at the rate that you would like to deal with soft IRQs, then K soft IRQD will go ahead and execute those pending soft IRQs. Okay? So you have two ways that they can be consumed, two ways that they can be generated. Depending on the way the system's behaving, it will just use one or the other to get soft IRQs taken care of. Okay? This is a pretty common approach in advanced operating systems, and they actually have different names. You have first level interrupt handlers and second level interrupt handlers, or Linux used to call them upper half and lower half handlers. So the handlers that execute immediately are the first level, and deferred execution handlers are second level interrupt handlers. Okay? I think this is kind of neat because really what we have here is we have a hardware mechanism that is very specific. I will say it's very constrained, but what we can do is start building abstractions on top of it that allow us to handle various situations, various hardware devices that may need either immediate or deferred responses, and we can go ahead and handle things when it makes sense for what our operating system needs to achieve. Okay? So I think this is pretty nifty. Any questions? All right, so that's that. Interrupting interrupt handlers. So yeah, if we can interrupt handlers, then it is very helpful, let me say, to keep track of how deeply nested we are. Because when we IRET from one interrupt handler, we may end up back in a kernel thread that's actually, or I should say a kernel context that is an interrupt context, not process context. So we have to be sure that we know where we are in these things. So Linux has a pretty simple mechanism where it keeps a counter called preempt count inside the thread info struct. And every time a hardware interrupt occurs, it goes ahead and increments preempt count. And when it returns, it decrements preempt count. So anytime you're in some kernel execution context, you can always look at preempt count to tell, am I inside an interrupt or am I just inside a trap where I'm about to go back to user mode? Okay? If I'm inside of an interrupt handler, I'm not allowed to do anything that delays, or I should say anything that passively waits. But if I am in process context, then I can do whatever I want. I can go ahead and block, and it's just going to block the process. It's not going to hang the machine. Okay, so that's an example of how Linux handles this issue of nested interrupts. Okay, so we have reentrancy now, and I already said reentrancy is really desirable in kernels. Okay, but we also have a situation that we could have the kernel preempt itself or not preempt itself. And so you might have heard the term preemptive kernel, non-preemptive kernel before. Let's talk about what that actually means. When you look at how the execution of a kernel thread progresses, typically in most kernels there is a specific point in the code where context switches can occur. Okay? So let's say that I'm going through my execution, I do something really slow, I say I want to open a file, I want to receive data from a socket, something like that. The kernel sets that up in the trap handler, and then it gets to a certain point and it's like, do I have nothing else to do? Yes? Okay, switch to somebody else. And that'll happen at a specific point in the actual flow of that code path. Okay? So if we have that situation where the kernel always performs context switches after it's done doing whatever it needs to do, then we call that a scheduled process switch. Because it always occurs at a specific, widely understood point in the kernel code. Okay? And you'll notice this, like Linux, in the Understanding Linux kernel book has a picture where it's like, here's the flowchart, and it's like, do stuff, do more kernel stuff, do kernel-y stuff, and then at the end it's like, do I need to context switch? Yes? Okay, then call the scheduler and context switch to somebody else. That's a scheduled process switch. So what we're saying is the kernel is not allowed to preempt itself. And more specifically, kernel traps are not allowed to preempt other kernel traps. User mode code is not allowed to preempt kernel code. These are more specifically what we're saying here. Okay? And like I say here, this is not related to preemptive multitasking, which can be really confusing because they both use this term preemptive. But what we're really saying is the kernel allowed to preempt itself? If we can preempt user mode applications anytime, then that's preemptive multitasking. But if the kernel is allowed to preempt itself, then we say that we have a preemptive kernel. Okay, so preemptive kernels are allowed to context switch at a much broader range of locations rather than just this one point in the execution. And so we call that a forced process switch. So it can actually force a process off the CPU even when it's doing something in kernel mode on behalf of that process. So a pretty common kind of example for this is we have a process, made a system call, it's copying data out of some kernel buffer, let's say it's an I/O buffer, into the process's user space buffer that it is using. Okay. So it's doing that, and the kernel is spinning on some loop as it moves data out of the kernel buffer into the process's buffer, and some interrupt fires. Okay, and now some other higher priority process is allowed to proceed. Okay, let's allow this. And now process B actually bumps process A off of the processor, even though it's in the kernel and not in process A user space code. Okay? So this is an example of a forced process switch. Okay? And what this means is that process A was in the middle of doing something, or I should say the kernel was in the middle of doing something for process A, and we won't allow that to complete until we actually give the CPU back to process A. So when we switch back to process A, we actually stay in the kernel because we have to finish this operation, and then we can go back to the user mode code. Okay, so you can see that this is somewhat more complicated than having scheduled process switches. Yeah, so preemptive kernels can replace the currently executing process with another process at any time. And it's not really at any time, it's just at a lot more times than the scheduled process switches. Okay, why would people want to do this? Well, you can see here that if I have one process that's higher priority than another, it may be that because of my system constraints or my system requirements that I need to get that interrupt handler to run that other process as quickly as possible. So that's a situation where we might want to actually have kernel preemption. So that if the kernel is doing something for a low priority process, something important happens, I want to switch to the high priority process right away, no big deal. I can just go ahead and do that. Okay? So that's preemption. Now, yeah, so this is what I was mentioning before. It does increase the complexity of operations within the kernel somewhat. We have to be careful. Basically, you can still constrain when these forced process switches occur. So we broaden the range of when those things can occur. We don't necessarily just say anywhere because that makes it a little bit too complex. But we can greatly increase the range of areas where we can allow these switches to occur. Okay, so here's an example kernel with preemptive multitasking. A timer interrupt forces the current process off the CPU. Okay, that's fine, but I might be inside of a system call. Basically, this is the situation where a non-preemptive kernel versus a preemptive kernel makes a difference. So in a non-preemptive kernel, the timer interrupt handler says, oh, the system call is going on. I can't interrupt that because I'm a non-preemptive kernel. So, yeah, so if it's not in a system call, it says, I'll just invoke the scheduler directly. I'll just go ahead and force the process off and force another process on. But if I'm inside the kernel, then I set a flag. And the system call handler is responsible for doing its thing, and then at the end of the handler, it says, oh, that flag is set. I need to schedule a process switch. So can you see why it's scheduled process switches? Timer interrupt handler goes off, it does its thing, and then it sees the flag and it says, oh, somebody requested a process switch, so I'm going to go ahead and do that. Okay. Now, a preemptive kernel behaves just a little bit differently. It just goes ahead and invokes the context switch. It doesn't wait. It forces the current process off the CPU even if it's inside kernel mode code. Okay. So that's just that's the distinction between preemptive kernels and non-preemptive kernels. Okay, so there are situations where kernel control paths are never preemptible, and hardware interrupts are a great example of that. So remember, hardware interrupts must always run to completion. We have to get the CPU back to something else that can be blocked or deferred. And so if I have a hardware interrupt handler go off, and then something else, our timer goes off and it says, okay, you have to change process. Well, but I'm inside an interrupt context, so I can't actually just do that. So the way that these situations can be handled is, again, keeping track of your interrupt nesting level. Linux is a great example. I have that preempt count value. Oh, it's non-zero. That means I'm inside interrupt context. So if an event occurs that would cause preemption, well, you fall back onto that other behavior. You just set the flag saying, when you're able to, schedule somebody else. But I can't right now because I'm in interrupt context, so I'll go ahead and just do the normal way. So you can see that preemptive kernels kind of behave in a way that's a superset of non-preemptive kernels. Once you have non-preemptive support, so I have to set a flag that says time to reschedule, well then adding preemption isn't terrible, because you have to use the same mechanism sometimes anyway if you're allowing interrupts to overlap. Okay, so that's a little bit of a detail there. Okay. Alrighty, let's see. Now the next thing we're gonna do. Are there any questions about any of this preemption stuff? If you understand the basics of it, then that's awesome. That's really all I care about right now, because PINTOS is reentrant, but it's not preemptive. Okay? Everything in PINTOS is scheduled process switches. So if you at least understand that, and that means that hardware interrupts are not allowed to overlap, but hardware interrupts can interrupt software traps, you're golden. That's really the minimal that you need to understand for the assignments. Okay? All right, so enough about that. Let's start talking about the mechanics of this, because we need to understand what happens in the hardware to understand how these kernel control paths are allowed to interrupt each other. And it's interesting because it actually behaves very similarly to the CS24 threading lab. So I used to think that lab was dumb until I started digging into how operating systems work, and then I was like, wow, this is the best lab ever, because it actually follows very closely what you do in real life. Okay, so IA32, remember we have a stack per protection level. Thankfully, you don't have to set that up. It's all set up for you in start.s and all of that code in PINTOS. So the user process has its own stack, which gets stuff in it as the program executes. And then I have a trap. I intentionally trap into the kernel, or I get interrupted by a hardware interrupt. The timer goes off, a disk I/O interrupt goes off, then I switch into the kernel thread stack, and certain things are saved into that kernel thread stack. Okay? Now remember, again, we don't really talk about this because it's more in the context of scheduling. It's one of those connections that we won't follow right now. But each user process or each thread, if you have kernel-level multi-threading support, will have its own kernel thread stack associated with the user process stack. It's separate, but it's associated with it. And so the first thing that the processor does, since we're switching protection levels, is that it saves the old stack details. So the stack segment value and the stack pointer value. Okay? Yeah, and so like I say, nothing is written onto the user process stack. The user process stack actually stays basically untouched in this mechanism. Now, when you get into signal handling, that's where we really manipulate the user process stack in obscene ways. It's really quite exciting, actually. But the kernel thread stack is where all the action is occurring during these entries into the operating system. Okay? Yeah, and obviously when we don't change protection levels, those details are not saved. But the other details that are saved every single time are the flags and the location we were executing. Okay? Which is, since we're basically doing a far jump, we get both the code segment selector value and the instruction pointer value within that code segment. Okay? Minimal state. And of course, remember, these are the flags that were before the interrupt was dispatched. So interrupt flag is set. So maskable interrupts are enabled. But then the interrupt flag is cleared as part of the dispatch. So we haven't run into any differences yet, but now we start to deviate because certain faults actually also push another value onto the stack, saying, here are some details about what happened to cause this interrupt. The page fault interrupt handler is the most distinctive because it has its own error value that doesn't conform to any of the other faults in the IA32 architecture. So a lot of them push an error code, but the page fault handler is special. And so it'll push some details saying, were you trying to execute an instruction when the fault occurred? Were you executing data? Did you try to execute something that's in a non-executable segment? So were you trying to write something in a read-only segment? So it actually has a lot of details it stores in the error code. Now you look at that and you say, okay, now I have some interrupts that behave one way and the rest behave a different way. That isn't easy to write a general purpose solution for. So a lot of operating systems in these handlers, if they have a handler for an interrupt that does not push an error code, they'll just push a dummy value, like 0. Okay? And that way, all the interrupt service routines can have the stack in a uniform way when you get into the C code. You can always expect that there will be an error code. For some interrupts, it's important. For some, you ignore it. Okay? So yeah, that's in threads enter stubs if you're curious. It's exciting to look at it once, and then it gets boring. Okay, and since traps don't have an error code, a dummy value is pushed for those as well. That's a really good specific example. Okay. Now, of course, we have assembly code because we have to write it in a special way. We have to do an IRET at the end, and GCC doesn't know how to generate IRETs and all that kind of stuff. So basically, we want to write our ISRs in C so that we don't have to write them in assembly code. Who wants to do that? I presume none of you did that for your booter, except for the little wrapper part. But we do need assembly code to set up for the interrupt service routine, to acknowledge the interrupt at the end, blah, blah, blah. So the OS will have code that generates a stub for every possible interrupt on the CPU. Okay. The thing that happens after the error code is the stubs frequently push the interrupt number so that the service routine knows what kind of interrupt occurred. Now you might say, shouldn't it know that? And yes, in general it would, except if you have the same service routine handling multiple kinds of interrupts. That's what this allows. Okay? And since you might have a whole bunch of interrupts you don't care about, why not just register one interrupt service routine for all of them that basically says, I don't know what that interrupt was. You know, tell the OS developer that something bad happened. Okay, so, so lastly, since we're interrupting some other kernel control flow or maybe a user process, it doesn't really matter where this is. We had register state, so that gets saved onto the stack as well. We do the push A thing, push all the registers on, and so forth. Okay. If we have floating point support, then we have to push those registers on. If we have MMX support and things like that, then we may need to save those registers as well. There's a lot of stuff we might end up needing to save. Okay. But now the interrupt service routine can run without disrupting anything. We have all the previous processor state saved in the kernel stack, and we can go ahead and do whatever we want. And then we can just restore it off of the stack. Okay, so that's the idea. Are there any questions about this mechanism? Okay. Let's see. Yeah, so the other nice thing about this is that this section of the stack can actually be exposed as a data structure so that you can say, hey, what was the calling programs or the interrupted programs EAX value? What was their EIP value? What was their stack pointer? And you can actually manipulate that stuff directly. You may or may not realize, if you looked at this part of the CS24 assignment 7, but the advanced signal handling mechanism actually exposes a machine context, which is basically exactly this junk, so that you can manipulate it directly if you would like to. Okay, obviously it's copied over the user process stack. We'll talk about how that happens when we talk about signal dispatch, but this information can be exposed, and then when we return and we restore that context, it automatically gets saved into the appropriate registers, and we can actually affect the state of the user process, which is pretty neat. Okay, so I'm going to skip over that because we're going to run out of time otherwise. Okay, so yeah, and if we have a situation where an interrupt interrupts a trap, or an interrupt interrupts another interrupt, we just repeat this mechanism. The only part that doesn't occur is the first caller's SS and caller's ESP, because we're not switching stacks anymore. We're all inside the kernel over and over again. So we just save the flag, CSEIP, error code, interrupt number, register state, and now the interrupt service routine can do whatever it wants and it doesn't mess up the trap handler, and so forth. Okay, so I just talked about that. So you can see that this kernel stack size does impose a pretty important constraint. This does take some space, but you can definitely have like 2 or 3 or 4 levels of nesting of interrupts without causing the system to explode. So that's nice. But of course, the kernel code can't do anything like, I'm going to do recursion to traverse data structures or something inside the kernel. You can't really do that because you don't have that much stack. And you have to be very careful. Okay. But this is just sort of a peek into how we manage these kernel thread stacks, how they're utilized. Now, there's one part that we don't talk about at all here. How do we switch from one user process to another user process? Well, it's really easy. It's not complicated. We have one kernel thread stack. It knows where its stack pointer ends and blah, blah, blah. It's got a thread struct that describes that. We just switch to another kernel stack and do all the other attendant switching of details, like updating the MMU and so forth. And we restore that stack's context off of the stack. So we can switch between kernel thread stacks very easily. Now that part is called dispatch, and we aren't going to talk about it right now because it's a little bit aside from the story we're going to talk about today. So just be aware of that. That is the one part we haven't really talked about. Okay, so that's that. That's a little bit of the mechanics. So you can start ingesting that, and we'll obviously revisit it a couple of different times. But since we have this shared state manipulation, we clearly need to think about synchronization. So we're going to start talking about what primitives do we have, how do they work, how do we implement these things, and how can we use them. Okay? And obviously, since we have different control paths following different constraints, we have to think about those kinds of things. And like I say, you can't really solve problems of synchronization between kernel threads and these various control paths unless you understand what is allowed to interrupt what, when is it allowed to interrupt it, and what shared stuff is actually being accessed. So this sort of dictates what solutions you choose when you're trying to resolve synchronization issues. Okay? Pintos is a simple example. Like I say, maskable hardware interrupts can never interrupt each other. Hardware interrupts can interrupt software exceptions. Pintos is reentrant but not preemptive. So a lot of times, if we want to keep from having stuff overlap, we just turn off interrupts. That was easy. And then we turn them back on when we're ready to do stuff. Okay? And we get more sophisticated as we build up our primitives, but that's the simple way of dealing with issues within Pintos, because Pintos takes a relatively straightforward approach. Okay, so we can have these overlapping control paths we need to synchronize. You've probably heard the term race condition. Basically, you have multiple kernel control paths that can overlap logically, and they manipulate the same shared state, and the outcome depends on who wins the race. That's why it's called a race condition, because sometimes kernel thread A wins and you get one resulting state. Sometimes kernel thread B wins and you get a different resulting state. And unfortunately, they don't always happen, which is why we like you to test on QEMU and we like you to test with Box. And I applied the jitter patch so that you can make the hardware interrupts go at different times so that you can potentially expose concurrency issues more frequently and more easily. That's why testing is really important. This is also why they're frequently called Heisenbugs, because sometimes looking at them makes them go away. So you try to put debug output code, or you try to run it in the debugger, and the bug disappears, and you're screwed. You're sad. Okay? So these are the kinds of things that I'm sure you'll run into a few of them throughout the term. Okay, very simple example, one that we talk about almost always when we talk about synchronization issues. You have two threads incrementing a counter, and this is in memory, so we have to retrieve it, modify it, then store it. And you can come up with many different interleavings where this could cause a problem. So here's one simple one. T1 loads I, switched from T1 to T2, T2 loads I as well, so they both have the original value. T2 increments the register, T2 stores it back, So now I is I plus 1. Yay, that's good so far. Then we switch back to T1, and T1 also increments, but it's working with an out-of-date value of I. And then we store that value back into I, and we end up with I only being incremented by 1 instead of 2. Okay. In a database world, this has a name. It's, what is it, lost updates? Because one thread is writing a value, not aware that another thread has modified it. I wanted to show you this one. You may or may not be aware of this. Did anybody actually experience this blackout, Northeast blackout of 2003? That was caused by an operating system race condition. Yay. Okay. So the weather was hot, which I guess in the Northeast was like 85 degrees, which was kind of funny. But like it says here, there was a widespread power outage affecting 45 million people. Okay, so it was hot. People were running their air conditioners. You have these power lines. What happens to a power line when you draw too much power through it? It heats up. And what happens with the power line when it heats up? This is basic physics. Yeah, it expands, so it gets longer, and then it sags, and then it touches trees, and the circuit goes down. So then what happens? Well, you reroute power into neighboring lines, which then have too much current, so they start to get hot, they sag, and then they go out. So they had this cascade failure that was occurring in their power grid. And a big part of it was that nobody knew what was going wrong because there was a bug in that part of the system. Like it says here, they basically thought everything was fine for an hour, and the system was falling over left, right, and center. Okay? So, yeah, the alarm reporting system crashed, and so it switched over to a backup system, which, guess what, had the same bug, and so it fell over almost immediately. Yay for race conditions. Very exciting. Okay, so, yeah, the Ohio operators were making decisions based on old information because the reporting system had a bug in it. Okay, so there was an alarm system, like it says here, approximately 1 million lines of code. It took 8 weeks to track down this bug. Oh, I love it. Mainly because it wasn't me. I've had bugs that took that long to track down. It didn't make me happy. But anyway, this is what the manager basically said. It took a considerable amount of time to go in and reconstruct the events. In the end, they had to slow down the system, injecting deliberate delays in the code while feeding alarm inputs to the program. The bug had a window of opportunity measured in milliseconds. There was a couple of processes that were in contention for a common data structure, and through a software coding error in one of the application processes, they were both able to get write access to a data structure at the same time. And that corruption led to the alarm event application getting into an infinite loop and spinning. Like I said here, this fault was so deeply embedded, it took them weeks of pouring through millions of lines of code and data to find it. Ick. This is why it's so important to understand what can interrupt what. Now, if you have a system that complex, bugs do happen, and they are this difficult to find, and it just makes you sad. So, you know, it's too bad. But, you know, I don't know. This is yet another one of those examples of why systems programming sucks. Anyway, let's see. So basically, there's a thing called a critical section. We'll probably start talking about this more next time. But basically, what we need to do is make sure that execution cannot overlap in certain regions of code. We call those critical sections. And we typically use some kind of mutual exclusion mechanism that allows only one thread of execution into that region of code at a time until it completes, and then we can allow somebody else into it. And there's a lot of different tools. We're going to start doing a coverage of those things in the next 2 lectures. We're going to go through various issues pertaining to mutual exclusion and explore that topic in a lot of detail. So are there any questions? All right, so next time, like I said, we'll start talking about synchronization. We're going to continue our discussion of synchronization, and unfortunately, we're only going to be able to scratch the surface of it. It used to be that we had CS141. I don't think that's a class that's taught anymore. Anybody here heard of it or have taken it? No. So they started offering it when I was an undergrad, and it was really good. It actually runs you through a lot of these kinds of details, which is really valuable. And now that we don't really have a class like that, you kind of have to pick it up as you go. So I'm going to cover as much as I can in this lecture, which is not a lot, I'm afraid. We're going to cover some really basic things. And then when we start getting into some of the more concurrent and complex parts of the operating system implementation, i.e. virtual memory page table management and file system buffer caches and things like that. We'll take a lecture or two to actually walk through the implementation of those things from a concurrency perspective so that you have a better sense of how to approach them. Because, again, it all comes down to the question of what can interrupt what things might all be going on at the same time, how do I synchronize access to things so that everything works properly and successfully. That really is all it comes down to. It's just that, when you're a beginner with these systems, you don't necessarily realize all of the things that are going on at the same time and how to solve those problems. So I'll try to spend some time talking about those in the future. But we did introduce this concept of a critical section. Again, this is probably not new to you, but you have race conditions, which are just pieces of code where the result of the code or the outcome, the state after the code executes, depends on who gets to it first. Okay, so that's why we call it a race condition, because whoever wins the race seems to have the biggest impact on the state. And so we need to prevent these race conditions by imposing mutual exclusion on certain regions of the code. And those regions are called critical sections. So yeah, critical section and then mutual exclusion. These two concepts are very closely linked because obviously mutual exclusion appears in other contexts as well. But mutual exclusion is just a mechanism by which we can enforce a critical section. Okay? So you can imagine the critical section is going to be enclosed by some mutex lock, some mutex unlock, and so forth. Okay, and there's a lot of different tools. We're basically going to talk about just a couple. We already got to see how a mutex is implemented in CS24 in assignment 7, so I expect that you probably understand the concept. You have some atomic bit test and set, you have some atomic exchange operation that the processor ensures is atomic, and then you can use that to build a mutual exclusion mechanism. So not terribly sophisticated. On top of mutexes, you can build semaphores. On top of mutexes and semaphores, you can build condition variables, read-write locks, a lot of other very useful things. So we're not going to spend a lot of time talking about the more advanced mechanisms like read-write locks and condition variables because they tend to be relatively straightforward extensions of these things. But like I said, these locks will generally block threads from executing. So we get passive waiting, which is really what we want. We don't want spinning. We do it sometimes when we have to. And remember, spinning tends to be the recourse of interrupt handlers running on multi-core systems because we kind of have to. Okay, so so that's what I was just talking about. Let's see. So there are purely software solutions, which is one of those really surprising results. But this was actually one of the first algorithms. It wasn't the very first, but it's very representative of how to ensure that two programs can coordinate access, or two, let's say processes or some pieces of code that are executing that want to enter into a shared critical section, how they can actually make sure that mutual exclusion is ensured. And this is the outline of the implementation. So while true, the outer while is just these two programs are trying to do something, and it's very simple. We've basically stripped away all the non-relevant pieces of the program. And you state your intention to enter the critical section by setting a flag. Notice I don't actually state it here, but flag is an array with two elements in it. That's all we have. And so we have flag I and flag J. That's all we really have. And we say, I want to go into the critical section, but it's the other guy's turn. So they get to go first if they would like to. And then we busy wait in a loop. Okay, so that's the first strike against this approach, but you can take it and turn it into passive waiting, not terribly difficultly. If you have things like a halt instruction and interrupts and so forth, you can certainly do that. A few of you did that kind of thing on the second project. So as long as it's the other guy's turn, then I don't go into the critical section. But once one of these two conditions becomes false, then I can enter into the critical section because I know either the other guy said I can go into the critical section, or it's not their turn. It's my turn, so I can go into the critical section. Okay. Once I finish, then I flag that I am leaving the critical section, and then I go on and do my own thing. Okay. So this is Peterson's algorithm, and I'll mention that there's a couple of other ones that are representative of this. This is obviously very limited. We're talking two processes or two pieces of code that could perform things. That's not very exciting. And we have busy waiting. So this is a very primitive approach. But like I say here, PI can only exit the while loop, that is, the inner while loop, which prevents us from entering the critical section. We're not allowed to enter the critical section as long as, like I say here, well, let me see how I state this. I want to get the sense correct. Yeah, so PJ is outside the critical section, so flag J is false. So you can see that the flag value basically brackets the critical section. I set it to true when I want to enter. I set it to false when I'm out. So if the other guy's flag is false, they're not in the critical section. I can go ahead and do it. I can enter into this critical section. Or it's my turn. If either one of those is the case, then I can go ahead and enter the critical section. Okay? And we're not going to talk very much more about it. There's proofs of this algorithm's correctness and so forth, but we're not going to spend very much time on it. It is a representative example, and so when you hear people talk about software-based mutual exclusion, they frequently refer to Peterson's algorithm. There's a few other ones, like I have here. I can't remember the details of all of them, but they have variations to them. Now I can do more than 2 processes, blah, blah, blah. You have various details like that. Okay? But yeah, they all work basically the same thing. So there's 2 problems to this approach. The first one is an obvious one, that we have to busy wait instead of passively waiting. Well, that's just because we don't want to have all the complexity of interrupt handling and blah, blah, blah. Okay, if we had those mechanisms, we could easily make this passively wait instead of busy waiting. Okay, so that's not really the big issue. There's another much more serious issue, which is that on all modern processors, this will probably fail if we just code it up as it is. That's really bad. The reason why is because a lot of parts of our stack basically like to reorder instructions so that we get more optimal execution. Okay? So if I have a compiler that tries to optimize, we're running on a superscalar processor, so I have multiple components, multiple ALUs, maybe multiple addressing logic, multiple other components of my processor, then I need to be able to schedule instructions to maximally use all of those things. That may mean doing them in a different order than the program actually says. And in general, compilers are pretty clever about trying to make sure that when it picks a reordering, that the result will be the same, but the compiler has no idea about concurrency. Multiple things happening at the same time. It kind of views the program as a single sequential flow. So out-of-order execution is good in most cases, but in a few cases, it's terrible. Okay? And then processors themselves also reorder instructions, which is even crazier. Okay? The Intel processors are more than capable of doing that now. So when we have these kinds of situations, you can easily end up with scenarios where out-of-order instruction execution or instruction reordering causes this software-based solution to fail. And that is no good. So thankfully, we have hardware-based solutions. We all know how to do those kinds of things with lock instructions and so forth. Not terribly complicated, but it turns out that those are actually a subset of a more general approach, which is that sometimes we have to make sure instructions actually execute in the order that we specify them. This is particularly true when we get into concurrent programming. When I want to do this thing, and then that has to finish, and then the next thing is allowed to start, and I'm never allowed to reorder those things, then I need to have some way of enforcing that. Okay, so barriers are a great example. Like I say, our previous software solutions don't work in the context of out-of-order execution, so we simply prevent out-of-order execution by putting a barrier between 2 operations. Okay? A barrier simply means everything before the barrier has to finish before anything after the barrier is allowed to start. That's all we really mean by a barrier in this context. Okay? I mentioned multi-threading barriers, not a terribly complicated topic, but I'm not going to waste the time to talk about it right now. You can ask me after class if you're curious. Okay? But in this context, we're just making sure that everything finishes before anything starts after the barrier. Okay? Now, there's kind of 2 kinds of barriers. We have barriers at compile time, and we have barriers at runtime. Because we have 2 places that instructions could be reordered. We could reorder them in the compiler, we could reorder them at compilation time, we could reorder them at execution time. So we have 2 places, and the compiler situation is fixed with an optimization barrier, which you can see is a very simple barrier. It actually does nothing if you look at it. We say, I want to emit some assembly code, and then you emit no assembly code. But then what you do is you tell the compiler that everything changed. It has no way of optimizing anything across that boundary because it can't make any assumptions about the state of memory. So let's say it sucked a value out of memory into a register. And then it was using the register to do the intermediate computation. And then maybe it would like to assume that that register value is still the same. Well, when you say that all memory is changed, then the compiler no longer can trust the value in that register anymore. Now memory may have a different value than the register holds, so it has to go and fetch it again. So that's the concept of an optimization barrier. Really simple, right? And so you can put barriers into your code. Thankfully, you guys don't have to. I just want to state this up front. This is really important for understanding concurrency on these systems, but it is thankfully not required for you guys. I would love to give you an assignment where this was required, but it would probably be several weeks, and you'd be pulling your hair out, and we don't have time for it. So sad we don't have semesters, right? So anyway, you just make sure if you have some part of your program that needs to be completed before the next part can start, you just insert a little barrier there, and then you can trust that the compiler will not reorder instructions across that boundary. Okay, so that's the idea behind an optimization barrier. Okay? Of course, just because you say the compiler is not allowed to do it doesn't keep the processor from doing it. So we have to make sure we also tell the processor that it's not allowed to reorder across that boundary as well. So optimization barriers are necessary, but they're not sufficient. So memory barriers basically prevent instruction reordering in various ways at the processor execution level. Okay? Like I say here, all the instructions before the memory barrier must be completed before any instructions after the barrier are allowed to commence. Okay? So that's pretty easy. And like I say here, when you want to emit a memory barrier instruction at the compiler level, so you put that in there so that at runtime the processor knows, okay, you're not allowed to reorder operations across this boundary. You better also put an optimization barrier there so that the compiler also knows to reflect that. So you have them in both places when you do memory barriers. Okay? And there's various kinds. Let me see if I actually talk about it. Yeah, I do. So you have read memory barriers, which basically mean you cannot reorder reads. So let's say I read A and then read B. And you'd think that most of the time it doesn't matter if I read B and then A. But if I read A and then based on the value of A, I do something with B, or I don't do something with B, then if I reorder those operations, I might have a problem. So I have to make sure that I put a read barrier there. Okay, so read memory barrier specifies a constraint on reads. Write memory barriers specify a constraint on write ordering. And then you have a general barrier which will prevent all reads and writes. I should say before the barrier, all of those reads and writes have to complete before any reads or writes after it are allowed to commence. Okay, so you have basically three kinds of barriers you could think about. Okay. There are cases where single core systems don't require barriers. If I remember correctly, IA32 is actually pretty nice about reading memory. Like IA32, so this is another thing that's specified in an instruction set architecture. Does the processor reorder reads? Does it reorder writes? And IA32 is actually pretty nice as far as reordering things. Like, it's a very well-behaved processor. It doesn't do things that are totally crazy out of control. It might reorder reads, it probably won't reorder writes, and it definitely doesn't reorder certain other things. And you can read all about that in the IA32 manual. Not every processor is that well-behaved, it turns out. The DEC Alpha is like the most notoriously badly behaved processor ever. And part of the reason why is because it has two data caches on the processor that aren't necessarily always kept in sync. So you might have one read, and you get a value, and then you do a write, and it updates the one cache, and then you do a read of that value, and you see the old value still. Okay? And it's allowed to do reordering of things. So it's like the DEC Alpha is terribly badly behaved, and you have to be very careful when you're doing these kinds of concurrency operations to make sure that the processor does things in a way that makes sense. You can look it up and read about it. It's funny because Linux's concurrency model is kind of defined by the DEC alpha processor and how bad it behaves, even though IA32 is much better behaved. Because, again, Linux has to sort of try to handle the worst case. It's got to go to the lowest common denominator, support that, and then everywhere else, it may not even have to emit instructions to get various kinds of ordering guarantees. So that's just one of those fun things about trying to support many different processors. Yay, right? Okay, enough about that. So IA32 has a couple of instructions a couple of 3 instructions you can use. So you have lfence, sfence, and mfence, which you can use for read, write, or all general purpose memory barriers. Okay, but those are not the only ones that actually impose barriers. This is only if you are doing specific things in a specific section of your code. If you happen to be doing other operations, like you have an instruction prefixed with a lock, that operates as a barrier, which is a good thing. IRET operates as a barrier so that you know that the interrupt handler's work is all finished before you go back to whatever code you pick up with, so you don't have to worry about reordering across that boundary. Okay, so there's various things that IA32 does to try to make sure that life isn't completely miserable for people trying to write correct concurrent programs. Okay? And when you have multi-core systems, it's also really nice, because if you have a fence, you may say, well, what if that's only on that one processor? That would be pretty lame. And so the processors, I should say all the cores in a multi-processing system or in a multi-processor system collaborate to make sure that when you have a fence, everybody sees the same behavior. They'll see the old value and then the new value. They won't see the new value then the old value, or some other weird arrangement of circumstances. Okay? So again, not every architecture guarantees this, but IA32's guarantees in this area make it a lot simpler to write concurrent programs, which is, it's hard enough as it is, right? Next time when we start talking about some of the really clever advanced concurrency mechanisms, you'll be like, oh, okay, yeah, it's really nice that IA32 makes our lives simpler. Of course, we also mentioned previously that disabling hardware interrupts is always an option when you want to prevent concurrent access. You're probably doing that, hopefully somewhat frequently, but not too frequently. It's like, where's the balance? Is always an interesting question. But this is if you want to prevent interrupt handlers from accessing state that you are also manipulating. So I'm doing it from process context. I want to make sure that the interrupt handler can't manipulate my shared state. So I turn off interrupts while I manipulate my shared data. And then I turn it back on, and now the interrupt handler is allowed to access it. Okay? The interrupt handler is not allowed to acquire a lock, so they should assume that they can have access to it. If you're in the interrupt handler, it's because nobody's accessing the shared data structure. That's kind of the presumption inside the handler. Okay? There was something else I want to say about this, but I forgot. So we'll see if I remember. Okay, so you all know how to enable and disable interrupts, STI and CLI. So set the interrupt flag, clear interrupt flag, and so forth. Of course, this will not disable non-maskable interrupts, but those tend to be pretty infrequent. Okay. And yeah, this is important. When you disable interrupts, it's disabling them on one processor. It is possible to turn off interrupts on all the processors, but it's a terrible thing because basically then all the processors in your system stop dispatching, and so you're going to see sort of an increased latency to responding to interrupts, and that's bad. People will perceive that. And so typically you try to design multiprocessor operating systems to only have to disable interrupts on the local processor if you ever really have to. So that's kind of a really important detail there. I'm trying to remember, there was something kind of important that I wanted to mention. Oh yeah, I remember now. Sometimes people look at this and they think, I've got 2 data structures that are shared between some program and some interrupt handler. If I disable interrupts, manipulate the first shared data structure, re-enable, and then do some other stuff, and then disable, and then manipulate the other shared data structure, and then re-enable, I'm okay. Well, maybe, maybe not. You need to think about if those 2 operations are related, and if somebody wants to see changes to one, they should also have seen the changes to the other. In those cases, you need to guard the whole thing. So you have to think about the right granularity of your critical sections for correctness. So if you have multiple things to manipulate, don't try to make your system more efficient by just guarding each little manipulation. You may need to guard the whole thing. So again, you need to sit down and analyze whether or not it's okay for some people to see changes to one thing but not the other. Those are the kinds of things you need to think about in implementing these concurrent systems. Okay, now we mentioned briefly spinning, okay? And so it is possible to disable interrupt handling on all the processors. You don't do it with the CLI instruction. Remember, we have these APICs on the processor, and what you do is you can tell all the processors to disable their APICs. So now nobody's getting interrupts delivered. Okay? You can do that, but it's a terrible approach, and you really only do it when you absolutely have to. So we talked briefly about spin locks, which is basically if the lock is available, grab it, otherwise spin until it becomes available. Okay? So we call that spinning because you're sitting in a tight loop checking on the lock. Okay, so you're checking on the lock maybe a few clocks, you're giving an interval of a few clocks, and then you check on it again, interval of a few clocks, you check on it again, and so forth. So you're really checking it fast, which means you're kind of expecting that it's going to become available really quickly. They only make sense on multiprocessor systems where the lock is only going to be held for a very short time. Okay? And like I say here, the assertion is that they make no sense on a single core system. Okay? Because either they're going to sit there forever, which defeats the purpose, or they're going to waste time. Those are basically your two options. You're either going to waste time or you're going to lock up the system. Those are basically the options when you have a spin lock. Okay? So the scenarios that prompt spin lock use is that you cannot context switch away, i.e. you're in an interrupt context. Now, that's not the only situation. I'll talk a little bit about that. The other scenario is that you expect the lock to be held for a very short period of time, and you don't want to context switch away from the process or the thread. Okay? It could be either one of those. You'll notice that the second one doesn't necessarily require interrupt context. Okay? How many people here have used Postgres? Okay, so if you've used Postgres on a multi-core system, you're using spin locks, actually, because the Postgres lock manager is pretty clever. What it does is when a transaction wants to acquire a lock, it spin locks for a certain period of time. Because the presumption is other transactions may be short and they may release their lock quickly, so why actually context switch away from that process? Why trap into the kernel? Why do all of that work when the lock may be released right away? So you spin for a little bit of time, and then if you don't get it, then you go ahead and switch to passive waiting. Okay? So that doesn't require being in the kernel. That doesn't require interrupt context. It's just a good idea when you're in a multiprocessor system. Okay? But the other scenario that we care a lot more about in the operating system is that we may actually be in interrupt context and we can't actually context switch away. Okay? So we can use those for concurrent access. Really simple example is timer interrupt. I kind of gave this example before, so we'll go through it quickly. Each CPU is executing its own timer interrupt handler. Their timers are not necessarily synchronized, so not a big deal. That's fine. But the interrupt handler may need to access shared state. And maybe this is the preemption interrupt, so that we can actually kick a process off the CPU, switch to another process. So since we do have shared state, we need to have a critical section to manipulate it. And so we can just acquire a spin lock. And if one processor is spinning on this lock and another processor is holding the lock, well, it's able to progress. It will eventually release the lock. So this spinning guy is able to eventually acquire the lock and go on. Because nobody ever passively waits. Everybody will eventually proceed. Okay? That's the idea behind using spin locks on a multi-core system. Now, are there any questions about this specific example? Okay. If control paths can be nested, then you can get into all kinds of hurt. So spin locks, you can see, are a very powerful tool, but they're a very limited tool. Okay, so let's say I have nested kernel control paths, and I have some state that's shared between a trap handler and an interrupt handler. And I decide to guard that state with a spin lock. Okay, the interrupt handler can interrupt the trap. The trap handler probably won't be able to interrupt the interrupt handler. Who calls traps from interrupt handlers anyway? That doesn't make any sense. So the trap handler acquires a spin lock. Good, I'm using spin locks. I'm trying to be clever, right? So the trap handler acquires a spin lock. It starts accessing the shared state, and then the interrupt goes off. So what happens? The interrupt handler tries to acquire the same spin lock. Can it? The answer is never. It can never acquire the spin lock. This is a classic deadlock scenario, actually. It's just that one of the resources is the CPU, which is kind of fun. Okay, we have a resource guarded by a lock, which the trap handler holds. It needs the CPU to proceed so that it can finish and then release the lock. The interrupt handler needs that resource, and it holds the CPU. So there's actually a cycle in the dependencies there. Okay? So basically the interrupt handler hangs, and your fan will probably turn on because it's actively waiting, not passively waiting. You probably have all, you've probably all heard your fan turn on. Probably not because of this, I hope. Okay, so what you have to do in the trap handler is disable interrupts and then acquire the spin lock. That should always go really fast because, I mean, unless you're on a multi-core system where somebody else holds it. Okay, so this is one of those interesting scenarios where if you're doing things and you have nested kernel control paths, you have to think carefully about what's allowed to overlap, and when it gets to execute, what resources may already be held. Okay? Now, I hope this doesn't scare you. To me, it's like super exciting and fun. Like there's all these puzzles when you write an operating system. And you have to think carefully about how to solve them correctly. Okay, questions? All right, so there's one example. So I've kind of beat this one to death. They're only useful on multiprocessor systems. They should only be held for a short time. That's kind of the whole point. Otherwise, you'd be much better off trapping into the kernel or passively waiting, something like that, incurring all the overhead of passively waiting. So, you're talking probably on the order of a few hundred instructions. If a few hundred clocks can go by before you acquire the spin lock, you're probably okay. Beyond that, you probably should actually switch over to passively waiting. If a critical section is only entered by control paths running on different CPUs, simple spin locks are probably fine because you'll never get that weird deadlock scenario that I talked about. If more than one control path on the same CPU can enter a critical section, you have to think very carefully about whether or not you need to disable interrupts before you acquire the spin lock. Okay? You probably could run into this situation if interrupt handlers are allowed to preempt each other as well. I'm going to leave that as an exercise for you because I'm lazy. Okay? You can think about that. Linux has a couple of different spin lock primitives because of these constraints. So you can see that spin lock IRQ and spin unlock IRQ disable and re-enable interrupts. Spin lock and spin unlock leave interrupts enabled. Okay? Or I should say they leave interrupt handling in whatever situation it might be in. I mean, if it's already disabled, then it'll just leave it disabled. Okay? But spin lock IRQ and spin unlock IRQ make sure that interrupts are disabled before they perform their operations. I'm sorry. Spin lock IRQ disables interrupts. Spin unlock IRQ re-enables interrupts. I should be more specific. Okay. So let's talk briefly about deadlock. There's a couple different ways to formulate it, but you can see that there's certain common themes that you have when you can encounter deadlock. And there's a lot of different systems that can deadlock. Operating systems happen to be one of those examples where it can deadlock. You try to design it so that it won't. Okay, and so the definition here, a set of processes is deadlocked if each process in the set is waiting for an event that only another process in the set can cause. Okay, well, so this is an event-based formulation. The event might be releasing the lock on a resource. Okay, so that's how you can take this event-based definition and turn it into a resource-based definition. It's not very difficult. But here are the requirements for deadlock. We have mutual exclusion, so we have resources that can be held in a non-shareable mode, and all of the resources that are held or all the events that can occur are mutually exclusive. I have a hold and wait approach where I acquire a resource and I don't let go of it if I want another resource and I can't get it yet. So I could also have an approach where I say I want to acquire a resource, or I should say I acquire a resource and then I want a second one, and if I can't get it, I just release everything. That would violate hold and wait. Then I have no preemption. So If I have a resource, I get to hold on to it as long as I want. Nobody can tear it away from me. Okay? I get to choose when I want to release it. And then the final constraint that produces deadlock is that you have a circular wait situation. So the set of processes P1 through Pn can be ordered so that P1 is waiting for something from P2, P2 is waiting for something from P3, blah, blah, blah. Pn is waiting for something from P1. Okay? If all these four situations hold, then you have a deadlock. Okay? So that's really simple. That's not terribly complex. Why is this even valuable to know about? Well, it's when you have this set of requirements, then you can look at how do I design deadlock out of my system, or how do I break deadlock when it occurs. If I can preempt a resource, this is what databases do, then I can break deadlock, because if some process is holding a resource that's causing a deadlock, I just take it away from them, and then I can clear up deadlock. If I have hold and wait, well, I can have a process relinquish all of its resources, and then I break hold and wait, and then I don't have deadlock anymore. If I can break circular wait, then I can also break deadlock. Okay, so deadlock prevention. You engineer the system so that it never occurs. This tends to be what we need to do for these kinds of systems. So typically what you can do is impose, let me see if I talk about this here. Yeah, no preemption. So if a process can't acquire a resource, you relinquish all the other locks you hold. People don't normally do this because it's way too complicated. If you have multiple things and maybe you waited a while to get some of those things, then you definitely want to hold on to them. So it's not very practical. But circular wait is much easier to control. Okay? You just have a total ordering on all of your resources you want to lock. And as long as everybody follows the same total order, it is not possible to generate a circular wait. Okay? Everybody is always waiting for something that somebody else has, but then there's some guy at the end of the total ordering that's holding stuff and not waiting for anybody before them. So you basically never have any cycles in your wait graph. Okay? Okay, so yeah, like I say here, that's usually not imposed by the operating system automatically. It's the programmer has to do that. So you have to think, basically, to prevent deadlock. Okay? Then you have deadlock avoidance, where the system basically looks at what you're asking for and says, no, you're not allowed to have this, because it would cause a deadlock if you did. Okay? So that's an interesting scenario. Okay, let me go through this. I don't actually talk about the banker's algorithm, but the banker's algorithm, the reason it's called the banker's algorithm is because it acts like a bank. Banks try not to give you money if it would actually put them into a bad situation. Okay, so the bank carefully considers whether or not it has the assets or the resources to grant your request, and if it doesn't, it says no. So that's why it's called the banker's algorithm. You can read about that on your own. Oh, and these are always fun. You have wound wait and wait die. Okay, so if you have two processes, and typically you can order them based on whether or not they've already acquired resources or who started first or something like that. So we have an old process and a young process. Wound wait is that if the old process needs a resource that the young process holds, the young process dies. Yeah, we wound them. Okay, if the young process needs a resource that the old process holds, the young process waits. Okay, so that's wound wait, and then wait die is similar. If the old process needs a resource that the young one holds, the old one waits, and if the young one needs a resource that the old one holds, the young one dies. Yeah. So anyway, these are basically two other approaches that will fail resource allocation requests so that you can actually avoid deadlock. Okay, and then of course there's deadlock detection and resolution, which we talk a lot about in CS 122, so I won't spend very much time on that. Okay? All right, so these are various approaches to deadlocks. I'm not going to spend very much time about it. For us, what we need to do is think very carefully about the order that we acquire locks so that we can avoid deadlock. So we kind of prevent them in our programming. Okay, any questions about deadlock? All right. Let's start talking about a few simple locking primitives just to make sure that we cover them. Semaphores are extremely common and they're incredibly valuable. I love semaphores. They turn out to be so incredibly helpful for coordinating operations between threads or between processes. Okay? And so typically you have a process who wants to acquire a semaphore. We'll talk about what that means. And it will block. It'll passively wait until the semaphore is available for that process to acquire. So you can't use them in interrupt context. That's not a surprise. You can't use mutexes in interrupt context either. And so semaphores have a count, basically, and you constrain it so that, for example, it can't be negative. So it can be 0, it can be positive. That's fine. And then you have a list of processes or threads that are waiting to acquire the semaphore. And you have two operations, wait and signal, or down and up, because that's basically how they're implemented. When you call wait, you try to decrement the semaphore's value. If it would go negative, you're not allowed to. Instead, you go into the wait queue. If the semaphores count, so if somebody calls signal, the semaphore count goes up. And if there's threads in the wait queue, you pull one out and you allow it to successfully acquire the semaphore. So the count goes back down and that process is allowed to proceed. Okay. Edgar Dijkstra had some interesting names, mainly because they're in a different language, I guess. But you had try to decrease, again indicating what the value represents, and then you had increase, okay, or the Dutch versions of those. I can't remember what nationality Dijkstra was. Maybe wrong. Okay, so anyway, that's basically how these things work. So you can think of the value as being how many times can I wait before I block. So you can initialize the semaphore to 5, you could initialize it to 1, you could initialize it to 0 if everybody should always start waiting by default, and then you just signal to wake people up. Okay. So simple version, while the semaphore value is 0, add the thread to the waiting list, passively block the thread, and when that while loop finally terminates, the semaphore value will be positive. You know it will not be 0 or negative, and you go ahead and decrement a value, and off you go. Okay. Signal, again, you add 1 to the semaphore's value. If the waiting list is not empty, you remove a thread from the semaphore waiting list and unblock it. So now it's able to proceed. So it would have passively blocked there, and then, in signal, you wake it up, and it suddenly sees, hey, the value's not 0 anymore, and then it decrements it, and it goes back to 0. Okay, so that's the idea. You guys did this in CS24, so it's not terribly complicated. But you do have to enclose those sequences of operations in critical sections. Okay? And obviously it's a little bit more complex than that, because when you passively wait, you need to exit the critical section so that other people can enter it, and then when you wake up, you have to re-enter the critical section. So it's a little bit more complicated than we have here. But I think it's straightforward to figure out. And there are various ways to manage the block threads. So you could always put them at the end of the waiting list and always take them off the front. That tends to be a very simple way of doing things. You could choose a random thread to unblock. That seems kind of over the top. But it's interesting because you don't really have very many guarantees of fairness here. Okay? It's certainly possible that somebody waiting can be preempted by somebody else who comes in and calls wait at the right time. So we don't really guarantee fairness with these data structures. Most of the time, these concurrency mechanisms don't guarantee fairness because it's more expensive to impose fairness than to just let it be unfair or possibly unfair or whatever. Okay? And that's fine. If you design your algorithm so that you don't care about every block thread getting access eventually, then who cares? You'll be perfectly fine with a partially fair or unfair concurrency mechanism. Okay, counting semaphores, so you can think of that value as being a count. How many times can you call wait without blocking? So you could say how many instances of a resource are available, how many threads do I want to be able to run concurrently, those kinds of things. Okay, and so we call them counting semaphores when they're used in that way, and you'll notice that it doesn't really ensure mutual exclusion. So because you can have multiple threads or multiple processes call wait concurrently, and they'll all get access. And we looked at this example in CS24. It happens to be a really classic concurrency problem, the producer-consumer problem. What if you have one or more producers and one or more consumers, and they're running at various rates to produce and consume data? So how do we get those things to actually collaborate in an efficient way? So it's a very common, you run into this problem a lot in system implementation, it turns out. And so the simple solution we used in CS24 is you have one semaphore representing how much data is actually in the queue. So that tells you how many Readers can try to read data before they start blocking. Okay, so a writer signals every time more data is added. You have another semaphore that says how much space is in the queue, so writers have to get access to write before they can write, and it will again passively block if there's no space available in the queue. Now you might ask yourself, just as an aside, is this the most efficient way of creating a queue that passively waits both on readers and writers? And the answer is no. There's a couple of other more clever ways of doing it, but it's a very straightforward, comprehensible way of doing it. So not all that bad. We like things that are comprehensible. Okay, now of course we had two semaphores, and we have shared state, and those things need to be manipulated. But we said that when you have a counting semaphore, it doesn't ensure mutual exclusion. It just allows you to govern resource access. So we still need to have some way of guaranteeing mutual exclusion. We have to have some way of enforcing a critical section. And so we introduce a third semaphore to enforce mutual exclusion. Okay? And that allows us to govern the shared state within the bounded buffer to make sure that nobody can manipulate it. You know, it's non-atomic manipulation, so we need to guard it in a critical section. And we make sure that this semaphore will have a starting count of 1. So only one thread is allowed to grab the semaphore. All right? Now, when we use them in this way, we call them binary semaphores. Okay? So the maximum value of the semaphore is 1, and we can enforce mutual exclusion. Now, we're doing addition and subtraction. As we all saw in CS24, there are more efficient ways of guaranteeing mutual exclusion. Bit test and set, lock exchange, those kinds of mechanisms are more efficient than using a binary semaphore that increments and decrements a value. Okay, whatever. Okay, you can create more efficient systems. You know, if you just go in and create the specific tools. Okay, are there any questions about semaphores specifically? They're pretty straightforward, right? I mean, it's not terribly complicated. You've got a counter and you've got a list. How much more complicated can it get? Condition variables, which we won't talk about, actually are like a mutex and a couple of lists. It's only slightly more complex. We don't really talk about them, but you can figure them out on your own relatively easily. And I believe there's actually an implementation in the Pintos docs that you can look at and read about. So you have that to look at if you'd like. Okay, so since semaphores that are used as binary semaphores are a little bit expensive, we go ahead and use mutexes frequently to simplify the state management and make it more efficient. Okay? Now, if anybody ever asks, I don't know if anybody's ever asked you this question in an interview or something like that, but it's the kind of question I would ask in an interview if I were interviewing system programmers. What's the difference between a semaphore and a mutex? Okay, well, that's a good thing to think about. One of the huge differences is actually sort of a semantic usage difference. Mutexes, when they're acquired, are considered to be owned by whoever acquires them. So I own the mutex until I release it. Semaphores can be used in a much broader range of scenarios. Now, is this really like a constraint, a technical constraint or a limitation? No. It's just conceptually how people look at them. Semaphores, one thread can acquire a semaphore and another thread can signal the thread by, what do we say? No, we say we can wait on the semaphore, so I'm waiting, and then somebody else signals me to wake me up. A really simple sort of poor man's condition variable. Okay? You'll run into this a lot in Pintos in these assignments. On Project 4, when you actually get into user space and system calls and all of this stuff, you'll have an exciting situation where you start a process and then you want to find out if it's terminated yet. Well, what if the startup process takes longer than the guy who's waiting and he calls wait before the process is fully started? In those situations, your brain should always say, semaphore, I can use a semaphore. So you create a semaphore, count as 0. The parent waits, so he tries to acquire the semaphore. The child increments the semaphore after loading is completed and the process has started, or let's say the process is finished. Then you allow the interaction. So semaphores are a really great synchronization mechanism between processes, between threads. Mutexes are basically only used for enforcing mutual exclusion. Okay? All right, so yeah, they're typically formulated to block processes passively. So again, we have some queue associated with it, and because they passively block, I should say they block and make people passively wait, then they typically are not used from interrupt context. Okay? Any questions on this stuff? I know, like, this is a lot of knowledge, and as you use them, you'll start to realize, oh, this is how these things are useful, and you'll start to get a sense of how the tools are used. It's amazing. Semaphores are such a powerful tool, and mutexes are powerful too, but semaphores are really good for coordinating processes together. Okay, let's see. Yeah, we've only scratched the surface. That's basically like the two most basic things, but there's a lot of other stuff you could talk about. I mentioned barriers. I'm now talking about the multi-threading synchronization primitive. There's a lot of synchronization problems which are great to study. If I have time, which I doubt I will, so don't expect it, I would love to go through multiple solutions to the dining philosopher's problem, which again you may have heard of. I can't even remember. What is it? You've got a table and philosophers around it. You've got a chopstick on the left and a chopstick on the right. So every philosopher has a chopstick between them, or every pair has a chopstick between them. And philosophers are either thinking or they're wanting to eat. And so before they can eat, they have to acquire both chopsticks. So design a system that allows all the philosophers to eat without starving to death. Okay. So it's a fun problem, and I think it was actually designed for an exam back in the day. And there's a handful of solutions that are really, they demonstrate various approaches to concurrency. Let's see, yeah, so there's a lot more detail on deadlock detection. If you're curious, you can take CS122 and see how databases solve this problem. It's very different. And then there's a lot of other things that we don't talk about. What is live lock? Well, that's in a situation where everybody can try to acquire, and if they fail, they go do something else. And because the attempts keep happening at the same time, nobody ever actually acquires the resources that they need. So live lock is a weird situation where it's deadlock, but everybody's still moving. Okay? Movement does not always indicate progress. And a few other things. Okay? So, are there any questions? All right, so what I want to do, we have about 3 minutes left, and I don't know if I'll be able to get through all this material, but I did want to throw it up here. I wanted to talk about thinking like a kernel programmer because it is very different from thinking like an application programmer, and I wanted to kind of point out some of these details here. It's not just that we're right near the hardware and we don't have very many abstractions to leverage, and we have to do a lot of our debugging in emulators and things like that. That's not really the only issue. The big thing with kernel programming is you have to focus on efficiency. And you'll notice that there's a lot of focus on efficiency because any little change you make, and you'll notice a lot of the things that are mentioned in the slides are not big changes, but since they're used throughout the operating system, they result in a big impact. And there's a couple of reasons. One is that we have fewer resources, and the other is that the kernel runs it intervenes in everybody's life. So if we make the kernel incrementally better, there's a huge benefit to everyone because everybody benefits from it. Okay, a few details here. Managing a linked list of items, you'll notice that in an application, typically you separately allocate each node. You link them together. Yay, that sounds fine. Probably everybody here has done that at one time or another, probably even this term. Frequently, the linked list elements hold pointers to other data structures that are also separately allocated. You do not do this in the kernel most of the time. First of all, you don't have a general purpose allocator. And we'll talk about kernel allocators for 2 lectures. It's really fascinating, all the solutions. Okay? We can't lose the space that you need to have to manage the heap. Okay? And also, it turns out that kernels typically only have a subset of data. They have a very limited set of data structures that they tend to need to dynamically manage. So we don't create general purpose allocators. So it's not really a big point in having them in the kernel. So instead, we fold that data structure management into the objects that need to be managed. And again, if you've done any of the third assignment, you've probably already started to notice this kind of thing. Okay? The list pointers point to the next list pointer. They don't actually point to the start of the data structure, which is really weird. One reason is because I may have multiple kinds of data structures that need to be linked into linked lists. And of course, when you do this, you need to figure out where is the start of the data structure so that I can access the rest of it. And so there's actually little, list elem, I can't remember, or list entry. Pintos has a couple of macros for this kind of thing. And you basically know the pointer, and then you have to subtract the offset from the pointer to the start of the data structure so you can get back to the beginning. Now, it's a little bit deceiving, this picture, because A is actually at a lower address than B, and B is at a lower address than C, because typically the way C lays out data structures is the order of them in the struct declaration is increasing address values. Okay, so that's why we do this, subtract the offset instead of add the offset. It looks a little bit weird. Okay. Now the other reason why we like to fold this into the data structure and just point to the next pointers in the list is that we may want to have multiple linked lists that tie our things together. Really common, unfortunately, which means you can traverse things in different order based on which list you start at. Okay? So that's one of those unusual things. Why do we do this? Well, the reason why is because we want to avoid dynamic allocation, if at all possible, because we really don't have that facility. We want to avoid the overhead of managing dynamically allocated memory. We want to do things as efficiently as possible. So we do this crazy thing. But thankfully, we can actually wrap it in macros so that all of this stuff is simplified. Now, another question, of course, is do we actually need to dynamically allocate memory? So we had this example, and you may or may not recognize that this actually corresponds to the thread data structure and how it's managed in the threads.c. You have the anchors of your lists are statically declared in the C file so that you can just access them. And these data structures are actually at the bottom of the thread stacks so that we don't actually have to dynamically allocate them. We just put them in the space that we have to set aside anyway for the thread stack. So you actually end up with no dynamic memory allocation at all. This is the reason why we do this stuff, because we don't have those facilities and we wouldn't want them anyway. Okay, here's another example, which is kind of near to my heart. Let's say that we need to manage a linked list of nodes, and we know that the list has a maximum size. So we know that there's a maximum number of elements that we need to manage, and most of the time that list will actually be full or mostly full. So instead of actually dynamically allocating the elements, why not just, again, set aside a region of memory that is large enough to hold all of the nodes we might ever need. Hey, guess what? Static allocation is fast. And then I can sort of link them all together into a linked list just within my array. So now you've thrown away your heap management space overhead, and allocation is really easy. You know, you just go and take the first node off the free list, and you've got your next node. So that's way faster than calling into a heap allocator. Okay? This is a really common approach in a certain kind of page table management. Clock. Yeah, it's called the clock page eviction policy. We'll talk about that in quite a few weeks. So, but anyway, this is a very common approach for implementing that. Okay, interrupt handlers. So this is also important. We talked about this briefly last time, that you have a choice between working in interrupt context versus in process context. If you do it in interrupt context, everybody's affected. If you do it in process context, only that process is affected. So again, what should you choose? Well, it's really easy. You typically want to make one process wait instead of making everybody wait. Okay? There's a couple of examples in the third project, the timer sleep. So this is why it's a good example. I'm going to go ahead and skip over this just because of time. We're already late. But you can read about that. Okay. And yeah, you can look at that as well. I'm going to just go ahead and skip all of this. So basically, the whole point of kernel programming is that you need to think about efficiency much more than you do in a regular application. Okay? And admittedly, these things generate only small savings. But since this is the operating system and everybody has to use it and everybody's affected by it, a whole bunch of small savings add up really fast. And so these are the kinds of things that kernel programmers think about a lot. Can I avoid dynamic memory allocation? Can I move computation out of interrupt handlers so that the interrupt handler is really short and fast and into process context? Are there constraints on system behavior that I can exploit? And can I reuse fields or data structures for multiple purposes? So you'll have to read the slides corresponding to those to see the specific examples. But there are frequently solutions that are still maintainable, but give you significantly improved performance that you can leverage. So I wanted to make sure to include some discussion of that. It's like, why the hell are we doing this weird stuff? And this is the reason why. It actually has a big impact. Okay, if you have any questions, please talk to me afterward because I don't want to take up too much time. Next time, we'll talk about read, copy, update.